welcome to this session. Today we are going to talk about reactor and show you mostly like a bit of slides at the beginning, but then live demos of reactor in action. So, welcome. I'm Simon. I work for Pivotal on Project Reactor. And you can reach me on Twitter if you have any question at any point. Well, not during the presentation, but after.
And I'm Victor Grazi, and I work at Nomura Securities on core tools.
All right. So today we are going to talk about, it's a four-part talk. Do you want to sit down? Yeah, it's mostly, we'll do demos, but as a first part, we want to introduce you guys to reactive programming. So what is reactive? The basics of Flux and Mono, maybe a bit about marble diagrams too, which are an interesting tool to visualize this stuff. Then the concept of a cold flux and a hot flux. So that's the presentation part. And then we'll do some demos. So Victor will start with core library demos, how to, with a little examples, like counting letters in phrases, demonstrate the temporal dimension of some flux operators. There'll be also a demonstration of the hot sequence concept. And then we'll switch over and I will show you a bit about testing and debugging that stuff. And in the last part, I wanted to show you snippets of WebFlux and the new WebClient in Spring 5. So how does Reactor integrates into the Spring ecosystem, or this Spring framework. So, reactive programming. What is reactive programming? It's mainly about, let me just pause for a second because I have a clicker here and it will be far better. What is reactive programming? It's an alternate programming paradigm, actually, in which you have a simplified mean of coding, of cleanly coding asynchronous and event-driven programs. So what does that mean? It means we offer a rich API to declaratively construct asynchronous processing pipelines. And this is done in a way that is concise, error-free, and is especially adapted to high load and concurrency if you need that. And it all stems from the reactive streams specification. The reactive streams specification stems from an original problem, and Victor, maybe you can talk a bit more about that.
Sure. So the reactive project, the original RX spec was devised by Netflix, and they had a big problem. When you go on Netflix, you are not just looking at a screen full of data, you're looking at a large number of requests, right? You want to find your movies, you want to find your favorites, you want to find advertisements for things that you potentially want to see. So there are a lot of requests that go in to compose your master request. So how do you do that? So, and return something consistent, right, and aggregated. So Netflix came up with the original RX spec, where they're able to put everything into streams, and then we'll see more in detail how we're able to manipulate these streams and modify them and transform them and accumulate them. And so there's so much rich APIs we've been seeing throughout the conference, but what we're going to do today is really dig into some of this stuff.
Yeah, and if you want to get your hands on that stuff and start experimenting with it right away, you can, of course, get it on Maven. Reactor as a main artifact reactor core on these coordinates. There's also a reactor test artifact to help you test that stuff, so a test-only dependency. And if you want to get it on Gradle, that's the standard way of getting it. So yeah, but first you need to understand the basic model of Flux and subscriber, and Victor, you can talk about that.
There's kind of a learning curve that goes on with this reactive stuff. When we think of programming, traditional programming, we are dealing with objects. So we're manipulating objects, we're adding objects together, things like that. You really have to transform your mindset when you're dealing with reactive. So in reactive, we're dealing with flux. A flux is a stream of objects. The way it works is that a flux contains data, it publishes data, and you have to have a subscriber that listens to that data and does something with it. Everything is a stream of messages. So the flux emits the messages, the subscriber reads those messages, is able to extract data from those messages. Everything is a message. So even query results, computations, errors. Yeah,
even events and errors. It's just, so yeah, everything is an event. So it could be UI interactions, it could be query results, it could be computation. And the interesting part is errors are a first-class citizen in that model too. So the way it goes is a subscriber receives notification. And what is a subscriber? It's a very simple interface with only 3 methods. OnNext gets called, that's the way the subscriber gets notified of a new piece of data. OnComplete is how the subscriber gets notified of the termination of a sequence, successful termination. And OnError is how it gets notified of a failure. So these last 2 are terminal events. After an error, for instance, there's no more data that can come in through the Flux. Also, a subscriber needs to be attached to its publisher. So once you get a Flux, you need to call the subscribe method with the subscriber. The easiest way to do that is through this variant of subscribe where you provide lambdas. So 1 lambda for what to do with each piece of data that comes in asynchronously. 1 lambda to define what to do with an error. So when there is a failure, you receive the error and maybe you want to show it to the user or do something else. And sometimes you want also to get notified of to do something rather when there is a successful completion. So the only real mandatory part is the how you deal with the value. Error handler is optional but heavily recommended. You have to think about your process. You have to think about errors happening in your processing. And handle completion is optional. Like it's rarer to do something, to have to do something at the end. Yeah.
Okay, so how do we use these things? How do we take these flux things? And it's if you've taken linear algebra, it's like the transition of moving from a single scalar to a vector of objects. There's a lot of things in there. And now we're talking about manipulating a flux, a whole vector of data. So how do we do that? So first of all, there are all of these operators. So a very common one is the filter operator. And what that does is it takes the original flux, it looks at all the data, it applies a predicate in the form of this lambda, and then it creates a new flux with just the data that matches that predicate. So in this case, we're saying persons. We have a person's flux, and it's got a lot of person objects in it. And we're saying just pull out the ones where the person is an adult, right? So what this is going to do is it's going to return a new transformed flux containing only the original objects from the original flux, only the ones that are an adult. We also have, similarly, we have a map operation. What is a map operation? It's nothing like Java util map at all. What it does is it maps according to a lambda translation function. So in this case, we're taking a person object and we're replacing it with a person's name. So the original flux might be a flux of person, and the result might be a flux of string. And of course, we have to have a subscriber in all of these. We can also gang these up into a fluent kind of API. So you're calling in this case, we're calling filter, we're filtering out adults, and then we're calling map, we're getting the person's name. So this is returning us a new flux of adults, names of adults. Every operator returns a new flux. So a flux is immutable. Every time we do a transformation or any kind of operation on a flux, we're returning a new flux.
Yeah, so a way to visualize that is through what's called marble diagrams. So these are pretty standard now in the reactive world, but it's a way, for instance, to document the operators. So what you see here is a source flux at the top, this arrow with the marbles in it. The marbles, the circles, represent the data, so on next events, basically. The vertical bar is an on-complete event. It's the end of the sequence. And then you see how, for instance, this is from the Java doc of the buffer operator. So once you apply the buffer operator, it says, OK, this basically will take the elements from the source, aggregate them into a buffer, and emit that buffer at the end. So it's a way to visualize operators in the Java doc, notably, to get a better sense of what it does. Interestingly, there is a site called rxmarbles.com, which it's more for RxJS operators, but there's a lot of common names and common concepts. So you can go to that site, and it will give you interactive marble diagrams you can play with and move the source elements around and see how it impacts the resulting sequence. Keep in mind that all of this is asynchronous. So it's not like Java 8 streams. We'll get to that later on. But these elements can come like 1 second apart or at random times. So yeah, keep that in mind. So what kind of operators do we have?
So some of the operators that we have are in terms of combining streams. So the merge operator says, OK, we have a stream that emits data here, and then we have another stream that emits data here. They're completely independent. We want to create a new stream that emits data anytime either of the other two streams or end streams emit. So effectively, what you have is a merged stream emitting all of the events of all of the composite streams. There's also a zip operator. I think we have pictures of these.
Yeah.
There's also a zip operator, so you can see that the first element in the first stream is a 1, the first element in the second stream is an A, so that produces a third stream that is the zipped result of those, so it'll put the 1 and the A together. And you notice that it doesn't matter the timing so much, it matters just which one is first, which one is second. So the 2 comes with the B, it produces a 2B, the 3 combines with the C, et cetera. So it's going in sequential order.
All right. We also have create kind of operators. It's more like factory methods, actually, where you can create a flux that will just emit a value that's called just. You can also convert any iterable list or what have you to a flux that will emit every single element independently in that list. Flux.range, it will emit integers starting from I, and it will emit n integers. And the interval one is interesting too. It's one of these operators that has a time dimension. It emits ticks from a clock. So in this case, every n second, it will emit an incrementing number. So you can combine that, for instance, with zip or something else with a different source of value to emit data at regular times, for instance. So yeah, that's a short presentation of the API and the concepts behind all that. And now we'll start live coding. Oh, Wait, that's a mishap.
Yep.
We also, yeah, sorry. I lied. We have also all sorts of operators, actually. We have transform operators that will allow you to skip a number of elements at the start of the sequence, or only take the first 2 elements and stop and cancel at this point. I don't know why we have this live coding slide in the middle of that. Yeah. Sorry about that. Other transformations include the filter and the map that we just saw. So map takes a function that transforms a T into a V and produces a flux of a V. There's a flat map. How many people have played with flat map in the Java 8 stream or in functional programming? Okay, so yeah, flat map has kind of the same signatures as map, so you might wonder what's the difference between map and flat map. That's usually one of the first questions that you ask on your reactive journey. So I want to dig a bit into that before we do all the live coding. Basically, map, it transforms one element into another element, and it's a one-one transformation. It does nothing in particular with these new elements. So it transformed from T to V, but it doesn't know anything about V. And that transformation is kind of synchronous. It happens right away. And map returns a flux of V. Flat map, on the other hand, it transforms one source element into actually a flux of potentially n elements. So it does a lot of, it applies kind of an inner asynchronous processing to each source element. So the function, the mapping function in flat map, it actually goes from T to publisher of V. But interestingly, as you can see in the bottom, it still returns a flux of V. So going from a flux of person to a flux of names. And despite having a signature that takes a publisher of names. So how is it possible and why? That's because flat map knows that you transform into a publisher of something. So it knows that it can subscribe to that publisher, and it will. Flat map subscribes to each generated publisher, and then it flattens the values of all these publishers. So think of it as an asynchronous transformation that you want to apply to each individual source element. And once you're done with it, you merge all the results, and you get a global flux of these results. Another interesting example would be you get a flux of strings, which are URIs, and you flat map into HTTP requests, and you get a stream of objects from the response. So that maybe begs another question. What's the difference between Stream and Reactor APIs?
So I think when I first looked at reactive, one of the things that really got me was it looks really like Java util streams, but they're really very different. So Java util streams are basically a way of iterating an iterable, right? An array or a list or something. And they look alike, but the reactive streams are really not that. They're really very dynamic, right? Java util arrays are very static. You have a fixed number of data. The reactive streams potentially have an infinite number of data. Regular streams, Java util streams are really very limited. They're pull-based, right? Whereas the reactive streams are push-based. There's no flow control in Java util streams. There's no concept of any kind of temporality, where you have all of that with the Flux. By the way, just the Flux over here, you notice the label says Flux mono. So Flux is a generalized container of a stream of a lot of objects. A mono is a subset of that. It's part of the contract is it will only contain 0 or 1 objects. So we use them interchangeably in some of the examples, as you will see. The other important thing between streams and fluxes is that a stream is really only, you can only use it once, right? You can't have multiple subscribers to a stream, whereas with a reactive stream, you can have any number of subscribers, and they're all pulling data from those streams.
All right. I also wanted to talk very briefly about the execution model and the concurrency of all that. So we have a scheduler abstraction that sits on top of, let's say, executor services, but it's an additional reactor-specific, or rather reactive stream-specific abstraction. And what it allows us to do is easily switch like execution context from one thread, or rather one scheduler, to another. And also it gives us the opportunity to do interesting stuff in testing, notably, with virtual time. And we'll get to that during the demo. But mainly, Reactor is kind of concurrency agnostic. The goal is for you to kind of stop worrying about all that threads and executor services and all that. But if you need it, then you can influence the execution context very, very easily and hop from a scheduler to another scheduler with publish on and subscribe on operators. So for instance, if you were doing a desktop application, like silly example nowadays, I know, but in Swing, for instance, or in JavaFX, you need to do all the UI changes in the UI thread. So this would be a good way of doing your processing in a background elastic pool of threads. And once you're done, emit the final result and display the final result in the UI thread using publish on at the end. So it gives you primitives to switch like that very, very easily.
Okay, so an important concept when we're dealing with reactive streams is cold versus hot. Very simply, a cold stream doesn't start publishing until there's a subscriber to it. Once there's a subscriber, that subscriber gets all of the data from that stream. A new subscriber comes on, it gets all of the data. So it's pretty much starting from 0 and ending at N for all of the subscribers. It always emits the whole set of data for each new subscriber, whereas a hot flux is kind of the opposite. It's when you think of live data, say a stock market feed or any kind of live feed, you'd attach that to a hot flux where new subscribers coming on will start receiving the data from when they subscribe, but the old data is gone for them. In order to create a hot flux, we can take a cold flux and we call the publish method, and that returns a connectable flux. And then when you get a connectable flux, whoever subscribes before you actually connect will receive the first emission and every emission after that until they unsubscribe. So you can see in this example, we're calling 2 subscribers, then we call connect. So they're both going to get all of the data. If you have a subscriber that comes before the connect, he's going to get all the data. If you have a subscriber that then comes after the connect, he may or may not get the first bits of data, but eventually they'll synchronize and they'll both start receiving all of the data that's pumped after the second one subscribes.
So yeah, this time for real, we are starting the demo. So let's see a bit of the core library in action. Yeah.
Okay, so what we're going to do now is look at some of the basic operators that we're going to use for reactive programming. So in the first case, let's start with the most simple example. And we'll take a flux, and the flux itself has a lot of these static operators that we can use to create all kinds of things. So let's create a flux, and I'm going to ask you to help me with this. And we're going to make a kind of a hello world flux. So let's run that. Very simply created a hello world flux, a hello flux. And it is not doing anything. Does anybody know why? No subscriber, so that's very good. So let's add a subscriber there. Okay, and the subscriber will just print. And there we go, we have a hello. Now this is overloaded, so we can take, it takes a var arg, so we can put a world there, and we can put anything we want, any number there. And that will create a stream containing those objects. Now let's take it one step further. Let's say we have a list, and I prepared one of these lists. So here We have this list of words. The quick brown fox jumped over the lazy dog. And we want to create a flux from that. So we just learned about the just method. And let's pass in our words over there. And of course, we're going to subscribe. We're going to subscribe. And let's see what that does. So does anybody see anything wrong with that? It's printed out the entire list as one element, right? So how do we fix that? So there's the just method is not exactly what we want over here. We want the from, and it used to be called from, but now they changed it. They broke it into from iterable, from array like that. So let's turn it into a from iterable, and that's going to give us, there we go, the quick brown fox, our phrase. Okay, very good. Now, there's a lot you can do with composing these kind of things. So let's say we want to add line numbers to this stuff. So how do we do that? So let's zip that. We're going to zip it with a new flux. And we're testing you now. So one of the operators that we looked at before was called the range operator. And what that does is it issues a range of integers. So in this case, we're going to issue the range from 1 to 100. And then we have to give it a lambda to say how we want to merge those. So we're going to take a word from the first flux. We'll take a line from the second flux. We'll provide a lambda that says, let's print the line. And then we'll print the word. So that should give us, thank you to IntelliJ for formatting that for me. And that should give us a list of the words that we want with the line numbers, and we see that does, right? So we have jumped over the lazy dog, 9 words. Now, I know when I was a child, my parents taught me that that phrase gives you all of the letters in the English alphabet. So let's see if we can actually prove that. So let's take those and convert the words into a flux full of just the letters of that. So we'll take the words, and let's say we want to map that, and we'll take a word, and we'll replace that word with we'll split it. So let's say we split it, just using a blank, so it'll give us a nice split on every character. And now we hope to see all of the letters of the words. Anybody see what happened there? We're getting the arrays there. So this is a case where we actually do not want to map, but we want a flat map. So we want to split the letters, and then we want to turn the result of the split, we want to feed those back into the flux. So what we want to do here is we want to take a flux, and instead of from iterable, we'll do a from array, because the split operator returns an array, and now we have a split of all of those words. So instead of words now, we're going to get all of the letters, and we see we do, right? The quick brown fox, we see it's all there, and we have 36 letters. Now, what we want to do really is we want to, let's get the distinct letters and make sure that we really have 26 of them, right? So we'll call the distinct operator, and what that does is it returns a new flux with only the distinct elements from the argument. And over here we see the quick brown fox, and something wrong. We only have 25.
Maybe you want to sort to make that easier.
Yeah. So let us try sorting, and we will figure out
pretty easy.
Exactly what.
Haha, we have someone.
Spoilers alert. Very good. So we have 25 letters, and you are indeed correct. We have the RT, so we want to see if we can change that to jumps, and hopefully we get the right value back. And then we get out 26 letters, and we have our S. So we can see there's a lot you could do with that. Now, so far we've just looked at a pretty static kind of flux. Let's look at something that's a little bit more dynamic. So I work in the banking industry, and we deal with stock market feeds. And so we might have feeds that are ticking. We want to subscribe to those feeds very frequently during the week, right? But that costs money, it costs resources. There's not a lot of activity going on during the weekend. So let's say we want to slow down those feeds during the weekend. We only want to subscribe to a limited number on the weekend. Well, for this presentation, we don't want to wait till the weekend. So what I've done is I've created a little method called isFastTime and isSlowTime. They're just little operators I created locally. And what they do is they're telling my flux whether to tick slow or tick fast. So let's see how that works. We're going to make a fast clock and a slow clock. So we'll take a We'll call it fast clock. And we will take an interval, and we'll start with durations of 1 second. So what that will do is it'll emit every 1 second. So let's see if that does that. So we see it's doing that. Now, just one thing we want to do. Let's map that so we get some feedback about what we're actually getting. So we'll take a tick, and we'll return it to, we'll say fast, and we'll display the tick. So that should give us fast and the tick. And then we'll be able to see which clock we're actually feeding from. Okay, very good. Now let's do the same thing, only we're going to call it a slow clock. And a slow clock is going to tick every 2 seconds. Okay, so now we have a fast clock that ticks every 1 second and a slow clock that ticks every 2 seconds. Finally, let's create a feed, just so that we have it. Well, actually, let's combine these two clocks into a big clock. So we'll call it the clock. And that, in order to join those two, we'll say flux, merge. And we're going to merge those two clocks. So we're going to take the fast clock, and we're going to
Yeah.
oh.
Yeah, extra closing
Sorry.
bracket. Yeah.
Thank you.
And also you want to make that.
Oh,
so.
yeah. Thanks. Okay, so we want to take the fast clock. We want to only filter that so that it only goes when it's a fast time. So we'll take a tick. You could call it anything, right? And we'll say is fast time. And then we are going to merge that with the slow clock, and we'll only play that when it's a slow time. So this clock, think about what it's going to do. It's going to tick at the times that it's a fast time, it's going to tick from the fast clock, and at the times that are designated as slower times, it's going to click from the slow clock. And let's just subscribe to that and make sure that it's doing what we think. They do.
No, you're missing the closing angle bracket from the...
Yeah, line 67, you're missing a closing bracket. That's what
Okay.
we did.
Live coding. So we see
And
the
now it's
fast
slowing.
ones are every second and the slow ones are every 2 seconds. So it's working. But how do we join that to our feed? So in order to do that, let's first of all, let's create a feed. So let's create a feed, just a simple one. We'll emit the time every second. So we'll call flux feed equals flux. We learned about the interval already, so we'll do it every second. We'll take it every seconds, and then we'll map that feed to a time. So let's say, okay, so this is going to emit
Need the lambda.
So this is going to emit every 1 second. It'll emit a time. So we want to merge that to our clock, though. So let's see. We'll test everything at the same time. So we want to take our clock, and let's try zipping that with our feed in such a way that we'll get a clock tick, we'll get a time, and we will display the time. We'll display the tick so that we can see if it's fast or slow, and then we'll display the time. Oh, and we want to subscribe to that.
Two subscriptions on there.
Do I? Thanks. So we see it's ticking every second, the fast time, and it is indeed giving us a time. And then it's slowing down, but something's wrong here. We got a 19, 20, 21. It should be ticking every 2 seconds on the slow time. Anybody see what's wrong with that? So as we said before with the zip, it's always pulling the elements in the same sequence, and that's not what we want. We really want to do with the latest from, right? So if we publish a later one from our feed, we want to pull that one with the clock. So let's try it one more time, and that'll give us with the latest. So we're up to 51, 53, and we see it is indeed slowing down.
Yep.
Okay. There's one more important point that we should consider, and that is how to attach to, let's talk about hot feeds, cold feeds, and about attaching to a real existing feed. So let's say I prepared an existing feed over here, and we just call it some feed. So we'll call it some feed equals new some feed. Now
so this is more like a listener-based or callback-based existing API.
This is an existing API, nothing to do with reactive. This is how we would do it in the old days. So we would say feed, we'd register a listener, we'd print out the event. This is all old imperative programming. Okay, and so you see that it's feeding up a lot of symbols. Do not buy any of these based on this because they're all made up data. Okay, now how would we do that if we want to transform this to reactive so that we get all the benefits of reactive, including the back pressure and being able to manipulate streams and control them? So in order to do it in the reactive way, what we want to do is use we'll create a flux. We'll call it feed flux. And that is equal to, we'll take a flux, and we call the create method. And the create method accepts an emitter, and it uses that to, we're going to create a new listener every time that happens. So we'll take our feed, we're going to register a new some listener, and every time a price tick comes in, we want to pass that into our emitter, which is a reactive, and we're going to call the next method on it. And we'll pass in that event. Similarly, when an error happens, we want to call the error method, and we'll pass in that throwable. Now, a really nice thing of this is that with this kind of strategy, you can pass in an overflow strategy. So you could tell it if you're overflowing, you're moving too fast, you could take the latest, you could buffer them, you could drop the results. In our case, we'll just take the latest. And now we want to subscribe to this, but before we do that, we talked about hot and cold fluxes. So this is officially a cold flux, so let's turn it into a hot flux. And the way we do that is we're going to call the publish method, and that will create a publishing flux, a connectable flux. And then we will call the connectable flux connect. But before we do that, let's just create a couple of subscribers, and we'll show that whether until we connect, nothing's going to happen here. So let's create that subscriber, then we'll call, let's say we call connectable flux, and then we'll say connect. Okay, and just to add a little bit of, so you know I'm nothing up my sleeve, we're going to slow this down a little bit. So let's say we sleep here for 2 seconds. Okay, so what we're doing is we're subscribing, sleeping for 2 seconds, then we're calling connect, then we're subscribing. So let's see if that, actually, let's do that beforehand. We'll do one after too. So we're doing sleeping and subscribing. Now we would expect that these would get data at different times because we're waiting 2 seconds. But since we're calling connect after, that's not going to happen. It's actually going to everything is going to start receiving the events from the underlying publisher in advance. So let's just run that and prove that that happens. Okay, so you could see that all of the events are duplicated or triplicated, right? 161, 109, 54. So we've seen examples of basic use of a flux. We've seen the temporal component. We've seen how to do a hot flux.
So let me switch over, and for the next demo, I wanted to show you guys a bit about testing, because once you start doing reactive programming, since everything is mostly asynchronous, since everything is mostly asynchronous, testing is different, right? So here I have a class that has methods that, as you can see, return mono and flux, flux only. So a few methods, an API, a service, if you will, that returns flux. How do I go and test, for example, this 10 to 0 method? So if I go to testing test, awesome name. Here I have unit tests that use the step verifier feature that I was talking about earlier from the reactor test artifact. And the way it works is you create a step verifier and you pass it any publisher. So in this instance, it's the result of this 10 to 0 method. And then you describe a set of expectations. So you say, OK, I expect that when I subscribe to this sequence, this 10 to 0 sequence, I will first receive 10. And then I will receive 9, 8, 7, 6, 5 in sequence. Maybe with an interval of 1 second between every emission, but that's the signals, the data that I expect. Then I expect to receive 4 more data signals. I don't mind which values. And I expect next. And this one is actually, I expect to receive a complete signal, and then I want to verify the whole stuff. So verify is important because so far you have only described a scenario, a test scenario, and verify will actually call the subscribe method on the 10 to 0 publisher. And it will let it play out, and if at any point the data emitted by this publisher differs from the set of expectations that you had, then the step verifier will throw an assertion error. And this is all blocking, so it doesn't, even if your sequence is using another thread, it will still wait for the end of the sequence before exiting the test. Right. This one is demonstrating a few other methods of setting expectations. You can even set expectations about the subscription event itself. You can perform assertions on a value. So you assert that the next value you receive is equal to 50, so using your favorite assertion library. So it's more of the same. So this one is here to show you that you can also assert errors. So this method takes an operation lambda, and you can see that this is a division. And since it's based on the 10 to 0 sequence, by the time 0 is emitted, it will try to divide 10 by 0, which breaks the universe. So here you want to check that actually this blows up and it terminates with an arithmetic exception that has the message divide by 0. So here we have another interesting short example. So in the names per second flux, what we have is a randomized list of sequence of names, and each name is emitted with a delay of 1 second. And here, in this test, if I run this test, I have 8 names in my list, and you will see that if I run this test, it will assert every data, but there's one problem. it takes a long time, like 7 seconds and a half. So this is a bit of a long time for a unit test. And if you are only interested in the values in there, it kind of sucks, right? So Step Verifier has a feature where you can, instead of using create, you can use with virtual time and lazily provide that flux that you want to test in a Lambda, in a supplier. And what this will do is this will allow you to shed the time aspect of your sequence and perform expectations only on the data aspect. So it gives you a virtual clock to manipulate, and that's what I do here. I say, for the next second, a virtual second, I expect nothing, and then I would expect the name summer to come up after 1 second. And then I will wait for 2 seconds, and by the time has elapsed, I expect to have received 2 more data, extra. And again, verify that it completes successfully. And if I run this test, boom, it's done. It's 286 milliseconds. And you can see that it printed instantly, if I replay it, printed instantly the whole set of data. That's an application of this scheduler abstraction. The fact that we are building on top of a scheduler allows us to do that sort of thing and inject a virtual time scheduler that we manipulate and trick into thinking that some time has elapsed. So this validates that this names per second really emits 1 item per second. It allows you to test that it contains what you think it contains, but it allows you to do that in a short time. Another question that often comes up is debugging. So here I have a main application that has, like, it doesn't matter what that does, but basically it has a flux of numbers that I subscribe to, and this flux has a fault. So if I run this application, it will, it's Spring Boot by the way, it will throw an error. It will say, oh, here's 10, here's 5, here is an arithmetic exception, you divided by 0. Okay, so how can I look further into this problem? If I look at the stack trace, does it help me really? I can click here and see that, okay, there's an operation, we divide 10 by y, so that's probably part of the problem, but where does that 0 value comes from? Okay, so if I dig into that stuff, at the end I only see a bunch of subscribe. So it's not really useful. The only part of my code that I can go to is this, and that's actually the point where I subscribe to my source sequence, but I don't know anything about where that numbers sequence comes from. And if I click here, it's actually injected, and if I go to, I have a class in my code that actually, I have a bit of a problem because I have 2 possible sources for that numbers flux, and that's flux 1 or flux 2, and both actually could produce a 0. So, how do I debug this? How do I find out where that error comes from? So, in a reactor, we added a checkpoint operator that we can add to that sequence and see if that helps. So if I add that checkpoint operator, I kind of tie that to a name like a unique enough string that I can search in my source code here and say, okay, this comes from this method, flux1. And it has a variant where if I pass this parameter, it will force the instantiation of a filling of a stack trace that will get reattached to the error. So if I run my sample again, now I get more information. So here I have my stack trace from before, but here I have an interesting piece of additional data. So it basically says Flux1 was the culprit here. So the error, the 0, came from this first method, basically. So it's not, it helps. It's not a silver bullet. We are still iterating on the debugging experience and tracing experience, but that certainly is a step forward when you want to debug a sequence and a complex asynchronous pipeline, right? Okay. So next, I also wanted to demonstrate a bit of WebFlux and WebClient. So here I have the skeleton with a lot of to-dos of maybe something that could be an endpoint or a controller. And let's see if we can make a reactive controller out of that. And if you're familiar with Spring MVC, this should look like something you know. So you can say, okay, we have a REST controller. Actually, I can use request mapping to say this has a root command, like API kind of URL. And I want to make an endpoint out of that method, so I can do get mapping. The name of the endpoint would be numbers. I don't want a list anymore. I want a flux, because that's the goal. We want reactive kind of stuff. I can make a request param like I used to. Actually, I can say, okay, is that required? No. And then here I can return directly from my service a flux. So 10 to 0 returns a flux of integers. I can simply return that. And if the operation I requested was divide, then I can do service.10 to 0, and I want to avoid error, so I can say on error of type arithmetic exception, maybe return just 0, fall back to a value. I wanted to map that to divide 100 by y. And that could give me an error, so I protect against the error here. Here I do the same with the multiplication, so service.10 to 0.map y 100 multiplied by y, and this should be fine. And as a default, I'll throw something. So if I run my application here, what's the error? I'll just continue doing the controller. I have another endpoint I want to make. Well, this one is pretty similar, so let's keep that one for now. But an interesting one is reuse this names per second flux. So I want to make a get mapping again, say, okay, this is going to be on the /names endpoint. And this is going to produce a flux of string, flux of names. So I don't need to block on that anymore. This will all be processed asynchronously. And how could I demonstrate that in the browser? Well, one good way would be to use SSE, server-sent events. And I can just do, okay, I want to produce text event stream, and boom, I have an endpoint that will translate to server-sent events of names. Oh, no. So if I go back to my application and run that application, okay, started. The first, so I had this number, nope, no, not that one. Numbers with an operation. I can do numbers 5, and this should, oopsie. Oh, that was number operation equals divide. And this gives me, returns me a list of the result of the division of 100 by 10, 10, 9, 8, etc., etc. And here I fall back to 0. And the names endpoint here, it's emitting live the data from the REST controller. So you can see that it emits one name per second, and you get it as a server-sent event, right? So that's pretty cool. Okay. The last part is WebClient. So Spring 5, you can use that stuff in Spring 5 and define REST controllers that are reactive. But even if you have MVC controller, it's interesting to get your hands on the reactive concepts by maybe using the WebClient to request an external API in a reactive way. Even though your controller is not reactive, the Spring framework will take care of that for you. But it's a way to familiarize with the API, basically. So I have a client example here where I create a web client on Star Wars API, a completely external API that gives me data about Star Wars characters and movies. And I can use the web client here to say, okay, instead of having a random mono, I can use the, that's swappy, yeah, the web client to say, I want to perform a get. I want to perform a get on this URI I have here. Say the character name, pass in the character name, and say retrieve the response and convert that into a map, like deserialize that into a map. And then I have prepared a flat map that will extract the meaningful value. I have also another method that I need to fill in here, so where I can use the web client to once again perform a get on this URL in the API, in the external API. I need to pass in the ID of a Star Wars character. Oh no. Character ID, yeah. Once again, I want to retrieve that, convert the body into a map, and the rest of my class will take care of extracting the data. So, of course, I want to return that. Okay, and here I have a controller that allow me to fetch. Basically, what this will do is you give it a name. Here, you give it a name. It will go to the API to fetch the ID corresponding to that name, do a search. And then it gets a list of movie IDs. And you want to, for each movie ID, you want to fetch additional data about the movies. And this will expose all that. This one will expose that as JSON. This one will expose that as SSE. So let's have a look at the SSE, actually. So here I have the okay, so here I have the version where you search by name, and if I run it, it takes a bit of a long time. If I give it the parameter Luke, it will first fetch, search for characters named Luke, detect, like return the ID of that character, and fetch each individual movie the character appears in. And it takes a bit of time. You get the result right at the end. Like if I do Han, it should give me the first 3 movies in the trilogy. Right. If I do that with a character ID, for instance, 1, I know that 1 is Luke Skywalker, we'll get a different view. So yeah, here you see that it's Norwegian to Google. Anyway, you could see that you could see the temporal aspect of it. You could see, thanks to SSE, you could see that first it fetched the name of the character corresponding to ID 1, and then live, as it became available, it emitted the names of the movies the character appears in. So if I do a random ID, yeah, and that's it. So this is a good way to basically get familiar with the API. You could do transformations on top of these body to mono calls. Like maybe you want to map that into something else, like extract value from the JSON. Here I used map, but the poacher that you would get out of JSON. You could use that as a way to familiarize with the APIs, and then start building your own reactive controllers, basically. And yeah, that's the demo of the WebClient and the WebFlux controllers. So yeah, that's pretty much it. We did all the demos, so that's the end of our presentation. If you have any question.
Next slide.
You can find the examples we just show you on GitHub. So here are the links, and of course, the slides will be shared pretty quickly, so you will get that from the slides too. Any questions? I don't know if we have time for questions. 5 minutes. So okay. So anybody got any question? Yeah.
The checkpoints for debugging, do I leave them in the code?
Sorry?
The checkpoints for debugging, do I leave those statements in the code? Even for production, or?
Yeah, that's something we really want to improve on, but for now, yes. The thing is, so initially it was something that you would activate at a global level, where every single operator in your application would go through this debug mode and would fill a stack trace, which is really costly, so you don't want to do that in production. We went from that to the checkpoint operator, where you can pick the flux, the sequences that are very critical, and you can prepare for debugging like that. And from there, we figured we could use a name, give it a name, and instead of, if you provide a string, we assume just a string, we assume that this is unique enough that you can do a grep on your code and find out where that comes from. So we don't do the stack trace stuff. And this is much more lightweight, so you could keep that in production. But now we have something called the context, which allows you to attach metadata to a particular flux, or rather even a subscription. And we could use that as a way to detect that you're in basically a testing context, and have a particular operator that you put in your chain, but it does nothing unless it detects that before you subscribe to the sequence, you have activated debug mode, basically. So that could be a way of doing that more dynamically. Yeah. Any other question? Sorry? Yep. Like the test doing nothing? Oh. Yeah.
That was something that I added. So at the end of those streams, if the application ends before the stream finishes pumping, it'll just end. So I added an after to just keep it alive.
Yeah, because it's asynchronous and there's a time dimension. It runs on a separate thread, actually. And as a result, if you don't do that, if you don't sleep or something like that, or the step verifier, by the way, will take care of that for you. But otherwise, the test or the main method would just exit, and yeah, so you don't see anything. Yeah. I had a yeah.
I just wanted to confirm, so suppose your existing libraries or code is non-reactive, but then you are using your own reactive library.
Yeah.
So the point at which you give the Flux some job to do goes out as a reactive
Yeah.
synchronously. Everything needs to go back eventually into your code, and you want to flog them. So it's a subscribe point where you have everything come back to, is there anything blocking?
So the subscribe method that we've shown so far, it's still in the asynchronous way of doing things. So as I was saying, if you subscribe and pass the system out as a lambda, like printed to the console, and you have an interval, for instance, that ticks every second, the control will still immediately return to your main code, and potentially it will exit and the application will terminate. But there's a way to bridge from the asynchronous world of reactive streams to the blocking world of like legacy services, or we provide a block method, block or block last in the case of Flux. So you use that and you get the result synchronously.
How does it scale? Like, I have a web application, use a WebClient, I have thousands of requests coming. If I start doing this, it's going to pick up a lot of packets in the JVM.
That's the whole point, is to be more efficient. So think of it that way. Nowadays, if you have like a lot of connections in a servlet model, you have to spawn one thread per request. And the default is basically Tomcat as a pool of maybe 200 threads, and then you will use that to serve your requests. Here, the default with Reactor and WebFlux, it's using netty at the network level, and it will default to like 4 threads and serve more requests per second with just 4. The trade-off is if at any point in a map, for instance, you block, like you do a DB call with JDBC, typical example, then you're in trouble because you are not only blocking your request that does this database call, you are blocking every single request potentially because the threads are shared. Basically, it exploits the like when there is a bit of I/O. Instead of waiting and doing nothing, the thread gets reused for other requests. That's the way it works. All right, thank you.